Section: Introduction. In this section, we discuss our approach to training large language models, LLMs. Typically, LLM providers create various models from scratch, each differing in size to meet different user needs. However, training multiple large models is very resource-intensive. Recent studies have shown that we can effectively reduce training costs by combining weight pruning with knowledge distillation. In our method, we only train the largest model from scratch and then create smaller models by pruning this larger model and using distillation to maintain accuracy. We successfully applied this compression strategy to two advanced models, Llama 3.18b and Mistral Nemo 12b, reducing them to 4b and 8b parameters, respectively. We made a significant adjustment by fine-tuning the teacher model on our dataset before pruning and distillation, which we call teacher correction. We found that skipping this step led to mismatches in data distribution, negatively affecting the distillation process. Our results show that our compression strategy produced an 8B model, MN-8B, that outperforms all similarly sized models on standard language modeling benchmarks. The LLM 3.1-4B models also demonstrated strong accuracy compared to the original Llama 3.18b model and the previous 4B model, with the width-pruned variant performing better than the depth-pruned one. In terms of speed, the MN-8B model is 1.2 times faster than the Mistral Nemo 12B model, while the LLM 3.1-4B models are 2.7 times and 1.8 times faster for the depth and width pruned variants, respectively. Our methodology begins with lightly fine-tuning the teacher model on the target dataset, which we refer to as teacher correction. We then apply pruning to compress the model and use distillation to recover any lost accuracy. For pruning, we focus on structured pruning, where we remove blocks of non-zero elements from the model weights. We assess the importance of each layer, neuron, head, and embedding dimension using a small calibration dataset. We employ an activation-based strategy to estimate importance, considering various axes simultaneously. For depth pruning, we evaluate layer importance using three metrics: validation loss, block importance, and downstream task accuracy. We rank the elements based on their importance and perform trimming of the corresponding weight matrices. Unlike previous approaches that used neural architecture search, we leverage insights from earlier work to guide our architecture choices. Section Summary. In this section, we describe our approach to compressing large language models, LLMs, by training only the largest model from scratch, followed by weight pruning and knowledge distillation to create smaller models, which we successfully applied to Llama 3.1 and Mistral Nemo, achieving state-of-the-art performance with significant speedups in inference. We also detail our methodology for structured pruning, emphasizing the importance estimation process and model trimming techniques used to optimize the pruned models. Section: Retraining with distillation. In this section, we discuss our approach to retraining after pruning, which we define as the process of recovering accuracy. We investigate two strategies for retraining: 1. Traditional training using actual labels, and 2. Knowledge distillation, where we use the unpruned model as a teacher to guide the smaller pruned model, referred to as the student. Knowledge distillation involves the student model learning to replicate the outputs and intermediate states of the teacher model. In our case, the uncompressed model acts as the teacher, while the pruned model is the student. We apply best practices from our previous research, focusing on minimizing the forward KL divergence loss between the teacher and student outputs. For our pre-training, we utilize the Llama 3.18b and Mistral Nemo 12b models, which were trained on proprietary datasets that we cannot access. The Llama 3.1 model was pre-trained on a substantial amount of data, specifically 15 trillion tokens. We begin our experiments with the base models available on Hugging Face. We use the NEMOTRON4 curated dataset for continued training in all our experiments. Our pruning method follows established best practices, as detailed in the methodology section. For width pruning, we apply L2 norm and mean as aggregation functions and perform single-shot pruning instead of iterative methods. For depth pruning, we drop a continuous group of layers that minimally impacts accuracy, based on insights from previous research. We skip the lightweight neural architecture search phase and manually configure the architectures for both LLAM 3.1-4B and MN-8B, drawing inspiration from the original models. We also address the issue of teacher correction, as using the Mistral NeMo 12B model directly does not yield optimal results due to differences in token distribution between the original and our dataset. To remedy this, we fine-tune the teacher model on our dataset using approximately 127 billion tokens. This correction is crucial when the original dataset is unavailable during distillation. We apply this fine-tuning to both the Mistral NeMo and LLAM 3.1 teacher models, noting that it has a minor impact on the teacher's accuracy across various tasks. For retraining, we focus on logit-only distillation, minimizing the forward KL divergence loss between the teacher and student probabilities while disregarding the language model cross-entropy loss. We utilize specific hyperparameters during this process and employ 32 NVIDIA DGX-H100 nodes for our training. Finally, to assess the instruction-following abilities of our distilled models, we conduct supervised fine-tuning on the Llama 3.1-4B models using the NeMo aligner with the instruction tuning dataset from NeMoTron4. We evaluate the aligned models for their performance in instruction following, roleplay, RAG-QA, and function calling tasks. Section Summary. In this section, we describe our retraining process after pruning, which includes conventional training with ground truth labels and knowledge distillation from an unpruned teacher model to a pruned student model. We also outline our pruning methodology, dataset usage, and the fine-tuning of the teacher model to better align with our dataset, ultimately employing logit-only distillation to enhance the performance of our compressed models. Section Analysis. In this section, we conduct a series of ablation studies to gain insights into the compression characteristics of our newer models. For width versus depth pruning, we observe from the training curve of LLAM 3.1-4B that width pruning leads to a lower initial loss and consistently outperforms depth pruning, even though both methods maintain the same number of parameters. Regarding pruning and distillation, we illustrate the benefits of our approach by comparing 4 scenarios. 1. Random weight initialization with distillation. 2. Random pruning with distillation. 3. Our proposed pruning with standard loss training. And 4. Our proposed pruning with distillation-based training. We find that pruning provides a significantly better starting point than random initialization, and distillation-based training is more effective than traditional methods, requiring up to 50 times fewer training tokens. When we look at teacher correction, we compare 2 methods. 1. Pruning and distilling a corrected teacher, and 2. Pruning the original teacher while distilling from a continuously corrected teacher. Our results indicate that teacher correction does not impact the effectiveness of pruning, and distillation from a corrected teacher is essential. We can perform teacher correction alongside distillation to enhance results. In our analysis of depth pruning metrics, we notice that as we remove contiguous layers, the validation loss increases, with the first and last layers being the most critical. Interestingly, removing non-contiguous layers can lead to even better validation loss. However, this does not always translate to improved performance on downstream tasks. For instance, selecting layers based on importance yields a lower accuracy compared to removing a continuous block of layers. We choose the latter method for retraining. For benchmarks, we evaluate our compressed models on various downstream tasks, including MMLU, human eval for Python code generation, and several question-answering datasets. We report performance metrics for different shot settings and use specific sampling techniques for our evaluations. In terms of base models, our results show that MN-8B outperforms similarly sized models, achieving better accuracy while using significantly fewer training tokens. The Llama 3.1-4B models also perform well compared to the teacher model, demonstrating the advantages of our methodology in terms of accuracy and training efficiency. For instruction-tuned models, we find that our LLM A3.1 to 4B variants exhibit strong instruction following and role-play capabilities, ranking closely behind Gemma 2 in certain evaluations. Our models achieve state-of-the-art performance in retrieval-based question answering and function calling tasks. Finally, we summarize some key insights. We emphasize that teacher correction is vital for effective distillation on new datasets, leading to a notable reduction in validation loss. We also confirm that teacher correction does not hinder pruning effectiveness and can be done simultaneously with distillation. Our findings show that we can achieve state-of-the-art accuracy with only 380 billion tokens post-pruning and distillation, particularly by focusing on width pruning while retaining attention heads. Section Summary. In this section, we conduct ablation studies to analyze the compression characteristics of our models, finding that width pruning consistently outperforms depth pruning and that distillation significantly enhances training efficiency while requiring fewer tokens. We also highlight the importance of teacher correction for optimal distillation and demonstrate that our pruned models achieve state-of-the-art accuracy with substantially reduced training resources. Section Mistral Nemo 12B to MNMINITRON 8B. In this section, we compare the Mistral Nemo 12B model to the MN Minitron 8B. Our compressed model shows better performance than the original on two benchmarks, GSM-8K and human eval, after we applied pruning and distillation. Specifically, the accuracy on GSM-8K improved from 55.7% to 58.5%, and on human eval, it rose from 23.8% to 36.2%. We believe this enhancement is likely influenced by the dataset, although we only retrained using the distillation loss. Next, we look at Llama 3.18b compared to LLM A3.1 Minitron 4b. Here, width pruning gives us better accuracy on the MMLU benchmark at 60.5%, while depth pruning results in 58.7% accuracy for LLM A3.1 compression. The reasoning ability is also affected, with GSM-8K accuracy at 41.24% for width pruning and only 16.8% for depth pruning. Depth pruning significantly increases throughput, achieving about 2.7 times the speed of LLM A3.18b, while width pruning offers around 1.7 times the speedup. We find that removing contiguous layers from the model during depth pruning is more effective than using non-contiguous, importance-based pruning.